Hello everyone, I'm Kangcheng from Tianjin University. I'm glad to share you with our study about how to use sliding window and machine learning method to achieve dynamic predictions and real-time optimization. The PEMFC Cold-Start is a complicated dynamic process involving multi-phase changes and heat exchange between the cell and the environment. During the cold start, the performance of the PEMFC cell can be changed by the cell temperatures and ice accumulation. However, to predict the PEMFC cell from the voltage reversal during the cold start, the cell voltage should be kept over a safe value. The flowchart of the PEMFC cell cold start optimization in this study is shown in this picture. We can see that the first developed two-dimensional PEMFC cell dynamic model is used to generate the data. Next, the machine learning methods are trained by the data and then coupled with a sliding method to achieve dynamic prediction and real-time control during the PEMFC cell cold start. Finally, the data-driven model is used to optimize the operating condition for the cold start. Sliding window method is widely applied in handling with time series data because it can transform the sequential supervised learning problem into the classical supervised learning problem. This figure shows the flowchart of the sliding window method coupled with ANN in predicting the dynamic process. With the help of those methods, the dynamic prediction and the real-time optimization can both be achieved. Those dynamic processes with different initial and operating conditions are used to provide the data for the machine learning. The overall evolutions of cell voltage, temperature, ice, ASR, and current density are shown in those 12 cold start processes. The dataset comes from 10 dynamic processes consisting of 451 samples for ANN training, which are divided into two parts, including a training site and a test site. Then the actual two processes provide 79 samples for the validation of the data-driven model. The predictive results by the data-driven model match well with the validating dataset. We can see those four pictures. Those four pictures show the validation of the data-driven model. Then, the K-fold cross-validation is used to further test the generalization ability of trained models based on the specific dataset. We can see that for the new trained models, the biggest average area of predictive results is lower than 8%. This accuracy of the model is good enough for the new predictions. Those four pictures show the average maps of cell voltage, ASR, temperature, and the electrical charge density. Through this data-driven model, a large number of dynamic process data can be obtained with low computational cost and high efficiency, which provides lots of information for the further optimization as well. The new and cold start predictions at different initial temperatures are shown in those pictures. This is a flowchart of the new strategy based on the data-driven model. Red two fingers show the influence of the original strategy and the optimal strategy on the cold start performance of the PEM fuel cell, and the specific evolution of the current density and the original and the optimal strategies are shown in this picture. It can be found that the cell voltage could be kept over a safe value in a whole cold start process by adjusting the current in advance by the new strategy. Those two fingers show the original and optimal strategies at different initial temperatures. It can be found that the new strategy has also been validated by the PEM fuel cell model, and the new strategy can enhance the cold start capacity of the PEM fuel cell and the lower initial temperature conditions compared to the original strategy. The new strategy can reduce the stop time of the cold start. In summary, the dynamic prediction and real-time optimization can be achieved by sliding window method and ANN. Then the proton data-driven model can be trained by the data from different multi-condition process. The prediction accuracy of the model is quite good enough. Thank you.